All right. I'm Brooks Davis. I work for SRI International and been working on the CHERI project for a dozen years now, almost 13 years. And yeah, I'm going to talk to you about what CHERI is and memory safety, why it's important, why it is in a sense, an existential threat to our community where we're writing in catastrophically unsafe languages, and how we can do something about it. So I got a question for the audience. What makes today of all days special? It's a historical event, 35 years ago. Anyone? Andy? Nope. Kirk? Nope. 35 years ago today, the Morris worm spread throughout the entire internet, taking down a whole bunch of systems. One of the several attacks that was used was a buffer overflow. So we've been dealing with these for a while. So let's talk a little bit about the history of the buffer overflow. So according to Wikipedia, buffer overflows as an attack were first documented in 1972 in a document called the Computer Security Technology Planning Study. If you ask my boss, Peter Neumann, he will tell you that Multics both identified the problem and solved it well before that. But that's usually the case for any security challenge. So we've known about them for a while. And as I said, it's in 1988, it was one of several exploits employed by the Morris worm. There was a buffer overflow. And I will say, actually, that I didn't put it on here, but probably apocryphally, there is some reason to believe that the first packet sent on the internet resulted in a buffer overflow and crashed the endpoint. So it's been around a while. So, and just as a little point on this, in history, 1993 is what we call as FreeBSD's first release. 1996, we had one of the first hackerly write-ups of buffer overflows, smashing the stack for fun and profit. So a classic paper on buffer overflow attacks. So we've had 50 years, right? So surely we've solved this problem. Unfortunately, not so much. A couple examples from industry. Well, industry progress, none. We're spending hundreds of millions of dollars. We've built great tools. We've fixed tons of bugs. And yet, here is a 12-year, 13-year span of vulnerabilities at Microsoft. Memory safety vulnerabilities, 70% across the board. You might look at this 2018 on the slide and say, oh, that's a while ago. Well, here's a recent graph from Google. It's 69% or either memory safety or use after free bugs. We're just making no progress whatsoever. And that's really depressing. So governments are taking note of this. So here's a bit of advice that came out. The US Cybersecurity and Infrastructure Security Agency, CISA, along with 10 other agencies across 7 countries, that's Five Eyes plus the Netherlands and Germany, endorsed this guidance. It includes the use of memory-safe programming languages. And as they point out in this guidance, they say basically things like address space layout randomization, control flow integrity, fuzzing, they're all great, they're all helpful. And at the end, they are failures. They do not solve the problem. So they say, move to modern memory-safe programming languages. Now, as a project that, as a project that's written in C, this is a challenge for us. And we probably need to worry about that. So why should we worry about that? Well, that's guidance, but when does guidance become regulation? One way it starts to become regulation is it becomes a procurement requirement. And usually, as happened with IPv6, it starts out as a requirement that you have to have a plan to migrate. And then, it becomes best practice, things become best practice over time, and then sometimes best practice becomes a requirement, even if it never becomes law that it's a requirement. And I'll give you a quick example of that. FTC versus D-Link. Federal Trade Commission saw that D-Link was doing an absolutely atrocious job. They weren't like the only players doing this, but by any means, but they were the ones who ended up on the sharp end of the stick. They were failing to secure their wireless cameras. They were using default passwords and exposing them to the internet. And in other cases, there were things like, so in this settlement that happened, I think the actual case started in 2016, and then in 2019 there was this final settlement where they agreed to fix a lot of things. They recalled a bunch of products. It was expensive, and as a result, there's an effective ban on, for instance, default passwords in consumer electronics. And in fact, I don't remember if it was this case or another one, but you can't have MAC address-derived passwords either, because those are trivially observable. So that put costs on manufacturing and whatnot, but it also helped consumers. So this is something we need to look to the future. So now that I've been scary about this, I'll give you a bit of hope. The next line in the CISA guidance is Secure Hardware Foundation. I wouldn't read too much into the words on this slide particularly. My understanding is this bullet point was added somewhat last minute and isn't the pitch I would make. But the pitch here is that there are hardware foundations that can get us to memory safety. And I'm going to talk more about CHERI and how it can do that. So CHERI. The short version is CHERI is an architectural extension that makes C and C++ memory safe. That means spatial safety at the C object level with some more effort, spatial safety at a sub-object level, as in when you access an array within a struct, for instance. And then with some operating system work, it also provides heap temporal safety. So CHERI is a processor architecture protection model. We compose a capability system model. Capabilities are a concept with long history and some successful adoption in FreeBSD. A form of capability that we've adopted is file descriptors as capabilities for system resources in Capsicum. And once you enter capability mode, you can only use capabilities to access system resources. You can't go and access resources. So you can't access resources by name anymore. CHERI capabilities are memory capabilities. They provide you access to memory, and I'll talk a little more about the details. But CHERI adds a new set of instruction set architecture primitives, and it's implemented in the microarchitecture of CPUs and system on chips. And it enables new behavior. So CHERI mitigates vulnerabilities in C and C++ code bases, in particular trusted computing bases, like your operating system. So hypervisors, operating systems, language runtimes, browsers. It's worth noting, for example, with language runtimes, Java is generally memory safe, but your typical JVM sits on top of 1 million lines, literally, of C code. And then there's the JNI, which gives you access to every piece of C ever written. So we provide fine-grained memory protection. That's the first line of defense and sort of the main point of my talk today, as well as scalable compartmentalization. And in particular, CHERI compartmentalization, when combined with fine memory protection, gives you orders of magnitude faster domain switches and allows for much finer-grained compartments. So now let's go down to the bottom. The core piece of CHERI is that we add a new hardware type, the CHERI capability. On a 64-bit system, this is a 128-bit, a new 128-bit data type. It extends the existing 64-bit address and then adds permissions and bounds, which control what addresses can be referenced and what operations can be performed. So a permission that doesn't have execute, for instance, obviously can't be executed. A capability, so if you have a read-write capability, you can read, you can write, but you can't execute. And so that metadata controls how these capabilities can be used. Capabilities are protected through a combination of tags and guarded manipulation. So the tag, which is basically a 129th bit, is separate and not directly manipulatable. So it is either, when it's in memory, it's off to the side, perhaps in an ECC bit, a stolen ECC bit, or perhaps simply striped with the data. It depends on your memory architecture that you implement in the system on chip. So if a non-capability operation writes to that memory, the tag is cleared. So if you store a word, if you were, for instance, you write a buffer overflow, and you write out a bunch of characters, and then you write over the capability, well, it's no longer a valid capability. If you then load it and try to access memory, that fails. Likewise, if you perform an invalid manipulation in registers, the tag that's in the registers is also cleared, and therefore that capability is no longer valid. Key point here is that all memory access in a CHERI system is via a capability. That could be an explicit capability, so you get a capability that you were given at runtime, and you've manipulated it, you've maybe chopped it up a bit for different allocations, and now you do a read. And you do it explicitly via capability, then you use that. But it can also be implicitly. And one of the key features of CHERI is that on a CHERI processor, existing code can continue to run. There's a default data capability and a program counter capability. And once those are set up, integer accesses can be performed. Now, in a mode where you have a default capability that's broad, say to the whole process address space, you don't really get a lot of benefit from CHERI, but you can still run your existing code unmodified on that processor. So that's the key value there. Now, to reiterate, the two key applications of CHERI, again, are fine-grained memory protection for C and C++. And so that's strong source-level compatibility. We are very, very compatible with existing C and C++ code, and I'll get into that a bit more later. We do require recompilation to gain the benefits of CHERI, but those benefits are quite strong. So in particular, we don't depend on cryptographic keys, which could be leaked or guessed, as with something like pointer authentication or ASLR. So every protection with CHERI is deterministic. And what we found in retrospective studies, if you take the CHERI protections, about 2/3 of memory safety vulnerabilities are eliminated. In practice, that's about half of all vulnerabilities in a typical code base. That's C or C++. We have modest overheads. In common cases, it's somewhere between 0 and 5%. In fact, we even see occasional benchmarks where we see negative, where we actually have negative overhead, but those are really probably benchmarking artifacts. Some pointer-dense workloads can be higher, and I will say that if you take me up on the offer to try it out later, I'll say benchmarking is complicated. But we have done quite a lot of work with ARM. We have spent countless hours on their high-end FPGA clusters to really nail down where the effects are, and the results are extremely promising. And then scalable software compartmentalization. This builds on memory safety, and it builds on the observation that what you can reach and access within a given address space is basically a transitive closure of your register set. So your register set has a bunch of capabilities in it. They can access more things in memory. You can load capabilities from there. But you can create disjoint sets of memory. And so you can have multiple compartments within an address space. So you don't have to pay context switching costs. You don't have to have TLB pressure. You simply have to make an exchange of your register set through some mechanism, and we have several mechanisms, but I'm not going to dive into that today. But those context switches can be extremely fast, typically easily below 300 cycles, much lower than even a basic system call. So we get enormous performance wins, and we think this is going to allow us to do a couple of things. First, make existing compartmentalization faster, but also to enable much finer grained compartmentalization. In fact, we're hoping to be part of a program. We've gotten a selection letter, but we're not in negotiation yet, that aims to add vastly more compartmentalization to a number of applications, so both kernels and programs, using automated techniques to explore compartmentalization boundaries, looking to add thousands of compartments. Whereas right now, if you look at something like the Chrome web browser, you have a compartment, you have a process per tab, and at some point, if you open too many tabs, you don't get more processes. And so things have to start being conflated. We want to have it to the point where we have a process per rendered object within the page, for instance. And we think that's possible. So for those of us who are, of course, building things with C and C++, what is CHERI C++ and how difficult is it to use? So CHERI C and C++ is really C++ with minor adaptations. A normal CHERI C++ program that isn't doing explicit capability manipulations like setting bounds and just relying on language primitives is a C or C++ program. It's completely compatible. However, you need to be clear about some things in the program. So we basically, to have a program work with CHERI, you need to do a somewhat more expressive job than you might have done otherwise. You can't just cheat and cast everything through a long. You can't cast your pointers to longs, do whatever you want, and then come out the other end sometime later, because a long is a 64-bit type typically, and a CHERI capability is 128-bit, and again, requires that guarded manipulation. So your types have to preserve provenance, and for instance, if you are adding two int pointer t's together, one of them needs to be picked. So the compiler will by default pick the leftmost one, and it will warn you. So you typically need to add a cast to make it clear which one it is, but it's really as simple as adding a cast or tweaking a type. Also, copying, because pointers go everywhere in C, copying of memory, like with memcopy, needs to be capability aware. This is fairly straightforward. Basically, you do the standard optimization that memcopies always do, which is they copy by words, except now you use capability instructions to copy anything that's capability aligned. The one surprising until you think about it for a moment, and then it's obvious thing, is that sort, like qsort, is a copying function because it moves things around in memory. So your sort has to be updated the same way. Again, these are the standard optimizations we make. So we just have to update them a bit, and typically everything's fine. The most naive possible implementation won't work, but it's not an issue. And then there are some cases where you need to do things like set bounds on memory allocations. And for those, you need to use compiler intrinsics to access those instructions. And those are the cases where your code does become not traditional C, but those changes are typically small. And in many cases, for instance, in our adaptation of the FreeBSD kernel, those changes can be hidden behind macros. So it's not even you're if-defing the code and you have one path for CHERI and one path for not. It's we have this thing that we do, and it's a no-op if you're not using CHERI. That's not the case for everything, but in many cases that is. And then the result is we have a memory-safe C. So it's spatially safe, again, at C object level. And then we can have sub-object safety with some additional work because there are some patterns that aren't compatible with sub-object safety. For instance, container of patterns or sort of pseudo-object orientation, which we use a fair bit in the kernel, can be a problem. But again, these are not huge. It's more work than a regular port. The result is still C. There are simply a few annotations that compile to nothing in a non-CHERI program. Otherwise, it works, works about the same. But we become a little less compatible with C. So in the sense that certain idioms have to change. And then with heap temporal safety, we implement that with a combination of the OS and the runtime. The observation that makes heap temporal safety work in CHERI is that because a capability has a base address, and while you can change that address, that base address, you can only move it up, and therefore you can always tell what allocation range a capability came from. And of course, because of the tags, you can always identify what is a capability, unlike in a traditional garbage collection system, where you could XOR a pointer with something to hide it. So we can actually perform reasonably efficiently, a scan of memory. That's unfortunate. Oh no, here we are, good. We can perform a scan of memory and sweep all of memory and revoke all pointers which have been deallocated. So I'd like to imagine a spectrum of software compatibility and talk about where CHERI sort of fits in things. You can imagine this, the status quo today. Security's not great. As I said, we've not been making a lot of progress there, at least in C programs. And we expend a fair bit of effort because we are finding and fixing these bugs. We are suffering all the time. We might, the simplified version of the CISA view is that we should rewrite it all in Rust. That's a lot of work. Maybe large language models help us there, or other techniques are going to allow us to rewrite our code, but there's a lot of code. It would be conservative to guess that there's 100 billion lines of C and C++ code in the world. Black Duck OpenHub shows somewhere north of 20 million lines of open source code. You can be fairly confident that there's quite a bit more out there. The supposed, I looked to try to find an answer to how much Windows source code is. No one wants to say, but one of the leaks did have more files than there are lines of code in FreeBSD. A lot of that's probably translation and things, but still. So we like to think that CHERI provides us a nice sweet spot on the spectrum where we can put in relatively low effort, adapting our code bases. We do have to pick new hardware, but that's a thing we do on a continuing basis. And we can get, with relatively little effort, we can get tremendously more security. So that is our hope with CHERI, and I think things are proving out there. So you might ask, well, how much work is it to adapt code? One measure of that is how much change do you have to make in your code. So here's an example. It's a slightly old table, but basically still accurate, of the overheads of changing the FreeBSD kernel and all of user space. So what you'll notice here is in every column, we're less than 1% lines of code change. In the kernel, we're looking at a bit less than 0.2% overhead, or lines of code change. And in fact, that number, I would say, is high, because one aspect of CHERI that we've exploited in our porting process is that we actually have two C modes. We have sort of the one I've talked about, where we make C memory safe and we make all pointers capabilities. We have another mode where only select pointers are annotated with capabilities. This has the advantage that you don't, for instance, have to fix quite so many things in some ways, but if you do what we did in the FreeBSD kernel when it was a hybrid program, we annotated every user space access and made every pointer to user space a capability. And that allowed us to have pure capability user space while still having a hybrid kernel. It aided porting. It has possibly some performance advantages, although we're still evaluating there. But it requires a lot of code changes, because now every time you have a system call that takes a pointer, you have to annotate every function that uses that pointer and every function that uses a pointer that might potentially be a capability. So there's a lot of churn there. So I would say this number is high. I don't have a good number as to what the real number is, but it's probably 0.1% or something if you did a completely pure capability kernel. You notice drivers quite small, 0.04%. The runtime, that's higher. We're almost a 0.5%. But that's where the memory allocators are. That's where the sorting functions are. It's where the signal handlers, all the horrible systemsy stuff is in libc, and so that's a higher amount of churn, but it's still not huge. Again, we're changing 5 lines in 1,000 there, and then like libc++, actually smaller, which is nice. In part, I think, because abstractions are better there, and also libc++ gets to build on top of libc, so much of the ugliness stays in libc. And then programs, 0.02%. So, almost nothing. And this number holds in a number of studies. So we ported 6 million lines of KDE to CHERI, and that, again, 0.02%. And much of that change was, in fact, fixing cross-compilation because it just wasn't working, rather than actually changing the source code. So yeah, to reiterate the adaptability thing, we require some small changes for spatial safety. We have to deal with the pointer size and alignment changing. We have to deal with preserving provenance. We have to clarify our pointer manipulation. And what I mean by that is, for instance, sometimes we do ugly things, like we realign a pointer to a buffer, or we stash bits in the low bits of something that we know is well aligned. It's a common trick. We also need to make sure we use correct types and types that mean something, because we can't just say, everything fits in a long, because a long is a register and whatever. We need a more mature model of the world. And then we need to tweak allocators a bit, because we want to put bounds on allocations. But it's worth noting that most programs don't need any of these changes. So most programs in FreeBSD required no changes at all. Even, sort of like a middle-of-the-road complicated thing like OpenSSH, I think the original version required 3 changes, and I think maybe we have no changes in the tree right now. I think we submitted 1 fix upstream that was accepted, and then the other ones were actually overcome by events because OpenBSD needed to fix the same things for different reasons. For instance, they used to pass pointers between the parent and child, but then they added a feature to re-exec the child to randomize, and then they couldn't pass the pointers anymore, and they had to pass indexes, which is what our code did. So that's pretty nice. And then there's a sort of less compatible but more secure option. So adding bounds to internal program allocators, you probably want to do that. You probably want to add revocation to your internal allocators, although maybe not. It depends on your programming model. And then subobject bounds are a little complicated, and in the strongest version of subobject bounds, we definitely actually disagree with what C says, so we make array access a little different, and we put bounds on references to array objects, which is definitely not permitted by C. So, and then temporal safety requires a bit more work, but again, we've abstracted most of that away, so there's libraries to help you out, and you only need to change the allocators. So adoption's pretty straightforward. So let's talk about hardware. So there's a number of different implementations of CHERI. We started out on MIPS because that was the 64-bit platform that was available and mostly patent-free at the time we were starting over a decade ago. We gave a talk about that implementation at ARM, gave a practice talk there, and some important people, Chief Architect Richard Gristlethwaite was in the audience, for instance, and said, this seems like a neat idea, let's talk. So in 2014, we started talking. In the fullness of time, this became the Morello, the Morello prototype. So the Morello project is funded by the UK government. They funded about $7 million into this. or 70 million pounds into this, and then industry put in a bit more than that to build this prototype architecture. They extended the ARM v8A instruction set with CHERI. They built a prototype system on chip based on the Neoverse N1. The Neoverse N1 is, for instance, what is in Graviton instances on AWS, and it's the basis, or varying generations of it is the basis for most of the super high-end ARM servers. And then they built a prototype based on the prototype board, and then we provided tool chains, and they provided tool chains, we provided an operating system. They have implemented GCC and have an early implementation of Linux as well. And so this is like a real thing. It's a 2.5 gigahertz processor, 4-core processor, and there's one here. I'm presenting on it. So that is the prototype. So how well does it work? Well, as I said, I'm presenting on it. I was going to do a demo right at this point, but for software reasons that are not CHERI's fault, I'm going to do it at the end. But right here, I'll show you this screenshot here, shows you a desktop where everything on here, all these pieces are memory safe. So it's KDE desktop. We have an editor, we have a debugger, and I'm using a memory safe presentation, well, PDF viewer. So there are a bunch of options for trying Morello today. We provide via our website, we have a tool called CHERI Build. It is a giant mess of Python. Thousands upon thousands of lines to build everything. It is our Swiss Army knife of build tools. The important point, though, is that you can download it. If you download it on a modern Mac, you can install a few packages with Brew and then with Homebrew or your favorite package manager, and then run one command and boot into a CHERI box in a couple hours. And it will build your whole tool chain, the operating system, all the bits. We also have available, if you talk to me or email Robert Watson, we have remote access at University of Cambridge. We've got a bunch of Morello boxes in a data center there. And one of them is actually part of the GCC compile farm. And any open source project can sign up and get on that box. They're like not super performant, so if everyone jumps on that box, everyone will be sad. But that is a system you can get access to quite quickly. You pretty much just need to send an email. Right, and we can provide jail access, or access to FreeBSD jails. Soon we're going to be able to provide Beehive VMs, but we need to merge the code. So we need to finish the reviews and get that in. We're hoping to have a release in the next week or so that will have that. And then in limited quantity, full system access is available. If you have a UK ARM, if your company has a UK ARM, I would suggest you go to the Technology Access Program website, and there's a request a board button. They have a few different options available under this program. It sort of ranges from you get a board and no help to some options where there's some funding available to do a particular specified project. Not a huge amount of money, but enough to subsidize a little R&D effort. In addition to that, we also ported CHERI to RISC-V as part of the DARPA SITH program. And something that derived from that work is a project that Microsoft announced earlier this year called Chariot. Chariot is a IoT focused, as you might guess, or very small system microcontroller. It's based on the very smallest profile of RISC-V, so it's 16 registers instead of 32. It is as stripped down as possible, and it has CHERI applied to it. So they've open sourced a core and a little microkernel OS that lets you safely run C and C++. They've also ported a JavaScript runtime to it, so you can have JavaScript in your light bulbs that's secured by CHERI. It's all very neat. And in fact, there will be boards available soon. They won't be ASICs this first round, but the low-risk project has been funded to build some demo boards, some sort of prototype boards, that they're going to give out 100 of them to various companies and organizations, and they're going to be available for purchase as well. So you'll actually be able to buy things and build, not with FreeBSD, because this is a microcontroller, but you'll be able to build CHERI microcontroller-based stuff and actually build real things. Kind of a neat thing on this board, you notice there's a lot of headers. So this top one is a Raspberry Pi compatible header, so you can put Raspberry Pi hats. There's this and this, I think, are Arduino headers. I don't remember what this one is, but there's be a bunch of connections. So you'll be able to build little things with CHERI and actually like control the world. And they're also going to build a fancier one based on OpenTitan. I couldn't find a date for it, but the Sonata is in progress. They've actually done initial board runs, like not real board runs, but like to get the connectors in the right place and make sure that things fit. So they're making rapid progress. So that's like a thing you'll be able to buy and try out CHERI. So that'll be pretty cool. And then some breaking news. 2 days ago, Codasip announced that they're a RISC-V IP company. So if you want to build a system on chip with RISC-V, they sell a number of cores. They're now selling a CHERI one. They haven't disclosed the full details, but I did ask, and what I've been told is that is a 64-bit application class core with an MMU. So I believe it was initially intended to run Linux, so it'll definitely run FreeBSD with modest effort. So like there's real hardware in the pipeline. So that's pretty cool. So like CHERI is becoming a real thing, something you can, heading towards something you can actually buy. I guess I will mention, since I've sort of been meandering through the various ports we've done, we've also developed an initial sketch of CHERI for x86. And we're in very early discussions with the x86 vendors about, could this work? And the goal here is that we be compatible across these ecosystems and be able to build on all the processor architectures. And we believe that's going to be the case. I think we've really demonstrated it with the MIPS, RISC-V, and ARM ports. Our code really doesn't differ except in the sort of grotty bits at the bottom. Application code doesn't vary at all. So yeah, I think we're making good progress there. So I'd be happy to take questions, and I can also show a little demo. I'll leave this up here for a moment, but and then I'll show some demos.
So
and I'm probably out of time.
no, we've got a couple minutes, especially since you started late. We'll bump the schedule by about the 5 minutes.
All right.
I had a question from someone on YouTube, which they asked, do you plan to support pure capability for the kernel and user space in FreeBSD /CHERI?
So I guess I would say that as soon as there is rational hardware to run on, like non-prototype hardware in the pipeline that we will be able to buy, then we will start looking at merging. It's going to be a project. I mean, unquestionably, it's a bunch of work. The diffs, well, I say the diffs are small, they are also broad. So review is complicated. We have review bottlenecks even internally getting features in. So it's going to be an effort, but yeah, we basically, as soon as there's going to be a platform to run it on, we'll be looking for ways to get it in. And while John's running the mic over, I'll just start the demo here. So I've got a little uname on the machine that I'm running on. So it's ARch64C, that's our name for ARM with capabilities. That's our default ABI, and we're running the PureCap kernel here. So memory safe, spatially memory safe kernel. So I'll take a question here now.
Right. So is this coming to the Intel AMD 64 world anytime soon?
Well, so we have a prototype. John's been the lead on that. It is the current state is that we have a user space instruction set model sort of basically worked out. We've got the core things. We have a proof of concept. I can't talk about partnerships at this point, but we're definitely attempting to talk to everyone and trying to bring it there.
Okay, and the CHERI organization, so are you more FreeBSD specific than anything, or are you trying to bring this to the entire world?
We're trying to bring it to the entire world. Our research group is our research group is fairly FreeBSD focused, both at SRI and Cambridge. But the goal is to take over the world and provide CHERI to everywhere. Right now, though, if you want to like build a product on top of a Unix, it's going to be FreeBSD. The ARM's Linux port is continuing to make progress, but they don't have the whole stack yet.
This is brilliant. Thank you.
For some context on x86, Brooks mentioned that we first engaged with ARM in 2014, and we got an initial prototype SoC. It's not officially a part of the architecture. It's just a prototype in 2023 or 2022. So that's like an 8 to 9 year lead time. And I would say that on the x86 front, we're not yet at the 2014 stage. So we'll have to see, but I don't think it's like years would be a realistic time frame.
So, while you run that mic over, I've run a little procstat-a here. So we've got a number of things. I think the thing I'd point out here is we have the emulator for a number of processes, ELF64C, which is to say that's the pure capability kernel. You notice we've got maybe one thing here that we haven't ported for whatever reason. We run that in hybrid mode as essentially an unmodified ARM binary. So yes, question.
You mentioned a little bit about performance impact, and these prototype chips. You said there's a 4-core chip.
Yeah.
How does performance scale when you get to over 100 CPUs or 64 CPUs? Something that the higher number, like a realistic large CPU count chip.
So, I mean, I'm not a microarchitect, I will say, but we don't have. I don't think there's any reason to believe that CHERI won't continue to scale. It is not, for instance, table-based. It is all a thing attached to memory. So we push DRAM traffic and cache traffic up slightly, both because our pointers are bigger and because we have to add the tag. But it's not like we're not adding new things that don't scale, or that you have to do lots of work to make them scale. We don't make cache coherency more complicated, for instance.
And to add to Brooks's point about those that are trying to get access, if you've got a UK ARM, etc. If you don't have a UK ARM, please come and see me if you're interested.
So yeah, we've got a custom CHERI, a CHERI procstat command. So I'm showing here. We have here that says what's the CHERI support in the process ABI. So P means pure cap. All these things with question marks are kernel. We have a quarantine, which is are we quarantining memory address space that has been released by the program, but where we haven't yet revoked it. That means, which is an indicator that the runtime is also engaged in revocation and temporal safety. There's a revoker state thing. It's always going to be none unless you really win a race and something happens to be running a round of revocation at the same time. And then there's the epoch, which is a number that moves monotonically forward as we go through passes scanning memory. So a bunch of zeros, but also a bunch of things. So like my PDF viewer here has run, a whole bunch of times, done a lot of garbage collection over the time, scanning all of its memory. So just a quick thing. So other questions? Yes.
Just any chance on this demo box you have a small C program that does buffer overflow to run it in hybrid mode and then to run it in capability mode?
I am not, so I don't know how to drive the part where I run it in hybrid mode, but I do have one set up. Oops. I will say this is the one thing that is not yet pure capability, is the Chrome web browser. We are very, very close. And I would say actually as a sort of testament to the difficulty of porting, we've had one person working on it for less than full time for about a year, and we're just about there. The biggest bottleneck lately has been a combination of he was off on another project and needing to port V8, and the V8 JavaScript runtime. So we're very close to having a pure capability Chromium. I don't know. So yeah, I will pull up quickly. We've got Kate browser here, or the Kate editor. And so in this example here, we have a simple program. We have a couple of buffers. We make sure that they're laid out the way you would expect on the stack, so we could overflow them. And then we write some stuff, and then we use this function to hide from the compiler the fact that we're going to do a buffer overflow, and we write one too far into the buffer. So let's go ahead and do a build. Let's see, build selected target, we'll do a clean. Target, build. There we've built, and then let's run. And now, it's hard to see, I'm afraid. But here we are. Programmers received a SIGPROT. It's a new signal we added, a CHERI protection violation, capability bound fault. And we see we're writing to this address is the capability. And we'll notice we've written to 16 off there, so 1 past the end, and we've got a fault. And so, yeah, I don't know how to run the demo with hybrid mode. Yes, so here we show the bounds and permissions. So this is a read-write capability store, capability load, so the default permissions for an allocation either on the stack or on the heap. And then, yeah, the bounds here. And so that's the dumbest example you can come up with. But example, yeah. Oh,
So as you were porting applications, have you ever encountered the SIGPROT, which was not a vulnerability, it was just happening sometimes, didn't affect the runtime? So I mean, did you discover any bugs during your porting to capability mode in KDE and so on?
So I mean, we have definitely found bugs, although fewer than you might expect. We found a lot of sort of weird off by ones that are mostly harmless. So I would say, I think my favorite example is one that we found fairly early on, is that if you hit tab for completion on an empty line in Tish, there used to be a bug where it would read 1 before the buffer. And with little endian architectures and whatnot, that's almost always a null character. So probably you never noticed, right? And there's a bunch of those, and I've exchanged a few messages on Fetty with some people at Apple who said, yeah, that's their experience with -f bound safe as well, is that there's a bunch of things that address sanitizer can't find because they're too small, and we do find them.
I found one for ARM64 when the 16K page support went in. There was a buffer overflow in writing to the VM page array or something like that Andrew committed that worked fine on plain ARM64, but crashed right away on Morello in QEMU. That was able to find an overflow that way. Yeah,
we also have found a number of cases in the kernel where forgetting to null terminate an array of things. So you would typically hit a null pretty quickly.
You hope.
Usually before something blew up. That sort of thing.
So I think we have one last question from Ed, and then we'll take our break.
And I will say, I'll be around this week. I'll go probably set this up over on the side somewhere so we can poke at it and talk about it.
Yeah, I'm just passing on a question that came on the stream, and the question is about, let's assume that commercially viable hardware becomes available. How would it get deployed? Like, what would the timeline look like, do you think? Or how would the ecosystem evolve, and how would CHERI hardware replace legacy hardware over time?
Boy, ecosystems are complicated. I mean, I would say that right now the strategy, what we're seeing is most likely is it looks like, despite ARM having first mover advantage here, RISC-V is going to have product out the door first. I think that's where we're going to see it coming, because there are a few motivated partners there, or few motivated players there, and there are some early deployments in discussion that are in, I guess what I think the term is first-party silicon, which is to say companies that make their own silicon are putting it into the parts of the silicon that they don't expose to the outside world. So they can put pre-standard stuff in, and it's a headache in the future if there's a standard version, but it's okay if it's not binary compatible with the next version. It's just something you deal with, right? So I think we'll see those first. Chariot, there's at least one product in development there. I believe a couple, and I know of at least one other project that I can't talk about. But they're sort of in the small side, roots of trust, that sort of thing. And then you move. I think we'll see things moving up. I will say the CODA-SIP, I believe, is sort of at the highest end of the CPU you might use in a root of trust. So, a significant application class processor, but certainly not, Neoverse.